Hi, Huckleberry here from PacketHacks.com, and today we're going to take a deep dive into the depths of TCP/IP. In this video, we're going to see what happens to a single packet as it is transmitted across the internet from host 1 to host 2. Host 1 and host 2 could be in the same country, in the same city, or in different cities. The process is still the same. Why is this important? Because it illustrates the basic process that allows data communication across the internet. If we didn't have this process, the internet simply wouldn't exist in the way that we know it. Suppose that host 1 is a client that wants to view a web page on host 2, host 2 being a web server. TCP/IP allows host 1 and host 2 to communicate across the internet, while it appears to the application processes on both hosts that they're directly connected to each other. Let's watch the packet get routed across the internet, illuminating the process by which routing occurs. The one packet that we will be looking at originates at host 1, then goes over to router 1, then goes over to router 2, then router 3, and over to host 2. This illustrates the path that one packet might take across the internet. In reality, there are many more routers between host 1 and host 2 than are shown in the diagram, and each subsequent packet sent from host 1 to host 2 could take different paths through any of these routers. This is what's known as packet switching, which is the method always used by TCP/IP. Packet switching is an entirely different method than circuit switching. In circuit switching, there is one path that all packets take, and this path needs to be set up prior to any communication. An example of circuit switching is the old POTS, or plain old telephone system. One thing to notice as we go through the video is that the MAC addresses change as they cross the internet, but IP addresses stay the same. For you noobs, we'll just note here that you have 32-bit IP addresses, which are at layer 3, or 48-bit MAC addresses, which are at layer 2. Let's see what's happening inside of host 1. Data from its application layer, which happens to be HTML information, is sent down to the transport layer. At the transport layer, we add a header to the data. This transport layer header has a source port of host 1 and a destination port of host 2. Note that the transport header, together with the data, is called a segment. That entire segment is sent down to the network layer. At the network layer, a header is added to the segment. This network layer header has a source IP of host 1 and a destination IP of host 2. So the source IP address is 144.44.44.1 and the destination IP address .77.77.1. Note that the network header together with the segment is called a datagram. That datagram, or the entire datagram, is sent down to the data link layer. At the data link layer, a header is added to the datagram. This datagram layer header has a hardware source address of host 1 and a hardware destination address of router 1. It's important to realize that the destination hardware address is not host 2. Note that the data link layer header, together with the datagram itself, is called a frame. This frame is sent down to the data link layer and is converted to ones and zeros and sent over to router 1 over physical cabling. Here, the frame is received at router 1. Router 1 looks at the frame and realizes that the hardware address matches its own, so it knows the frame is addressed to itself. Otherwise, it would ignore it. At this point, it removes the frame header, which it no longer needs, and the datagram is passed up to the network layer. At the network layer, the router looks in its routing table to see what the next hop is to get to 177.77.77.1, which is the IP address of host 2. In the routing table, it sees that the next hop is router 2. So router 1 sends the datagram down to its data link layer, and a new frame is added. The new frame header still has the same source hardware address of host 1, but now the destination hardware address is that of router 2. The frame is now sent out of router 2. Here, the frame is received at router 2. Router 2 looks at the frame and realizes that the hardware destination address matches its own, so it knows that the frame is addressed to itself. At this point, it removes the header, which it no longer needs. That's the frame header. And the datagram is passed up to the network layer. At the network layer, router 2 looks in its routing table to see what the next hop is to get to host 2. In the routing table, it sees that the next hop is router 3. The datagram is then sent down to the data link layer, and a new frame header is attached. This new header has the source hardware address of router 2 and a destination hardware address of router 3. The frame is now sent out to router 3. Here, the frame is received at router 3. Router 3 looks at the frame, realizes that the hardware destination address matches its own, so you guessed it, it knows that it's its own, so it accepts it, and it takes the frame header off. No longer needs that. And the datagram is passed up to its network layer. At the network layer, router 3 looks in its routing table to see what the next hop is to get to host 2. And in the routing table, it sees that the next hop is host 2 itself. So the datagram is sent down to the data link layer, and a new frame header is attached. This new header has a source hardware address of router 3 and a destination hardware address of host 2. The frame is now sent out to host 2. Here, the frame is received at host 2. Host 2 looks at the frame, realizes that the hardware destination address matches its own, so it knows that the frame is addressed to itself, so it's not going to discard it. But it does know that it needs to remove that frame header, so it does that. And then it passes the datagram up to the network layer. At the network layer, it sees that the destination IP matches its own. So at this point, it removes the network header, which it no longer needs. And the segment is passed up to the transport layer. At the transport layer, it looks at the destination port to determine which application process is supposed to receive the data. In this case, the port is 80, so the transport header is removed. And the data is sent to the HTTP application process. The HTTP process is now free to work on the data at its leisure. So what are the key takeaways? We see that as the frame goes from router to router, only the frame header changes. The IP header is looked at but never changes. The transport header and the data is never even looked at by the routers. The transport layer, along with the application layer, is called the end-to-end layers because they are only looked at by the endpoint hosts. But the network layer, the data link layer, and the physical layer are called host-to-host because these layers are looked at, although not necessarily changed, by every host along the way.